Hey, geometry students, welcome to an easy, complicated lesson. We're going to be learning about rotations today, and rotations really aren't that hard of a concept, but they kind of are. Okay, and here's what I mean by that. Now, first of all, when you use rotations, the easiest way to solve any rotation problem is simply to graph it, but not just graph it. Get out your graph paper, but also get out your compass. Because listen, when you rotate something, you're actually just moving the points around a center of rotation in a circular fashion so that the points always stay the same distance away from the center of rotation. Think about the definition of a circle. A circle is all points that are a certain distance away from a center. If you put your compass point on the center of rotation and trace a circle, you can see all of the points through which an individual point on a figure can rotate through. And then you can rotate it through certain degree measures. Okay. That's the easy way to do rotations. It's really not that complicated. But we're also going to be learning something a little bit complicated, kind of. We're going to be learning some ways that you can do calculations to just calculate rotations. Certain rotations lend themselves to being easily calculated, especially if you're rotating around the origin of a graph. But even if you're not, there's some calculations. Here's what I'm going to recommend. I'm just going to reveal for you quickly before we get into things. These are the four calculations that I'm going to show you how to do. We're only going to use a couple of these in the practice problems. I would recommend that you keep these handy somehow, though. So whenever you come up to a rotation problem, you know how to do a 90-degree rotation about the origin by formula, or 270 degrees, or 180 degrees. Even if we don't use them in this lesson, you should keep them handy so you know how to do them. Now, we've used the term center of rotation already. What is the center of rotation? It's the fixed point around which a figure is rotated. And as you rotate that figure, the points on that figure move in circles around the center of rotation. Rotation is an isometry. That means that when we rotate something, it's not going to change the shape or the size of that object. Okay. The points are just going to move in a circular pattern around the center of rotation. And then we have these formulas. If there's a point xy rotated 90 degrees about the origin, notice that these three, about the origin, about the origin, about the origin, these ones only work if you're rotating on the origin of your graph as your center of rotation. For 90 degrees, you just switch the place of y and x and make y negative. For 180 degrees, you just make both x and y negative. You're going to switch their positions. For 270 degrees, you switch the place of x and y again, but this time you make x negative. And then you could maybe ask, why isn't 360 degrees on here? Because at 360 degrees, it's just back to its original position. Okay. Now, I'm not going to go into why these work the way that they do. Maybe we could explore that a little bit in a future lesson. For right now, I'm just going to tell you these equations are sort of invaluable. These transformation equations are sort of invaluable for calculating some transformations. Then we have this last one. If a point xy is rotated 180 degrees about a point AB, oh, hey, if it's a 180 degree rotation, we have an equation here, a transformation equation that will let us rotate around a point other than the origin. Only if we're rotating 180 degrees, though, can we use this formula. So we have this special formula. Now notice what happens. We just do 2 times whatever the center rotation point, the x coordinate is, 2 times that minus x, and then 2 times whatever b is minus x. So maybe we'll get a chance to practice with that. Let's check out our lesson practice problems and see if we can apply some of these. Letter A. It says triangle ABC has vertices A, -2, -3, B, 1, 1, and C, 2, -1. Graph ABC and its image after a 90-degree rotation. List the coordinates of vertices A prime, B prime, C prime. Now, I'm not going to worry about graphing this here. I'm sure that you could do that yourself on a piece of graph paper if you want to see what this looks like. What I'm going to worry about is how we apply one of these equations. Okay. Now it doesn't say we're graphing about anything. It doesn't give us a point of rotation. So we're just going to assume that this is telling us to graph around the origin because it doesn't give us another point to rotate around. Okay. So we're rotating around the origin. And that means that I can use one of these about the origin formulas. What degree are we rotating? 90 degrees about the origin. So I'm going to use this one. And that means for each of the points, I'm going to switch X and Y. So that means that for A prime, let's see, I'm just going to do this in parts, okay? So the first thing I'm going to do is switch X and Y. It's going to be -3, comma, -2. But wait, I'm not done yet. I need to make the first value, so the original Y value has to become negative when I switch it over to the X value. So it's no longer -3. Now it's 3, -2. Okay, let's do B. B is going to be 1, 1, except I need to switch the sign on the one that gets moved over. So it's to be -1, 1. And then C is going to be, let's see, when I switch the -1 to the other side, it's going to be +1, comma, 2. All right. These are the coordinates of the rotated image after a 90-degree rotation. And I'm going to encourage you to just go ahead and graph the original points and then graph these points to verify that this is in fact a 90-degree rotation. All of these points should be the same distance away from the origin as all of these points. Because so if you use the distance formula, you should find that you get the same value for this from 0, 0 as you get for this from 0, 0. And the reason is because we just moved the points in a circle about the origin. We didn't change their distance from the origin. By the way, I think you can kind of visualize that the distance formula, which is going to be x2 minus x1, but x1 is going to be 0 because it was 0, 0. I think you can kind of picture that x2 squared plus x1 squared is going to be the same because we didn't actually change the square of the values of either of these just by flipping their positions, right? And it doesn't matter whether they're positive or negative because they're going to get squared in the distance formula anyway. So you could probably just, if you're in tune with the distance formula, you could probably picture that this is going to be the same distance from 0, 0. This is going to be the same distance from 0, 0. This is going to be the same distance from 0, 0. But I would encourage you to graph this one out and see how the rotation worked. All right, letter B. Triangle DEF has vertices D, 0, -2, E, 1, 0, F, 3, -1. Find the coordinates of the vertices of the image if it is rotated 180 degrees about the point R, -1, 1. Now, this would be an easy one to graph. All I would do is I would plot -1, 1. Then I would plot these points 0, -2, 1, 0, 3, -1. I would take a compass out. I would put the sharp point of the compass on -1, 1. And then I would put the pencil on 0, -2. And I would just draw a circle, a semicircle, 180 degrees around. And that's where I would plot my new point, my image of D. I would do the same thing for E, the same thing for F. But wait, we have an equation for this if it's not around the origin, but it's a 180-degree rotation. So we're just going to use our equation here. Here's how this is going to work. So D prime is going to be, let's see. So what we need to do is do 2a minus x, 2b minus y. So 2 times, for this one, it's going to be 2 times -1. That's A. This one's B, okay? Our point here that we're rotating, the center rotation point is going to be, its X and Y coordinates are actually A and B. So 2 times -1 is -2 minus the X on this point. Well, -0 is just going to be -2, comma. Now we do the same thing for B, for this point. 2 times 1 is 2, minus a -2 means +2. So this is going to be -2, 4 for the image of D. All right, let's take a look at the image of E. So again, I'm going to do 2 times -1 is -2, minus 1, that's going to be -3, comma. And then let's see, 2 times 1 is 2, minus 0 is just 2. negative 3, 2 is the image point for E. And then for F, the image point is going to be, let's see, negative 2, I'm sorry, 2 times negative 1 is negative 2, minus 3 is negative 5, comma. And then let's see, the image point for the second coordinate, 2 times 1 is 2, minus negative 1. Well, that's 2 plus 1, so 3. And these are my new images for my rotation of this triangle 180 degrees about the point R negative 1, 1. Okay, so that is how you do this. Again, I would encourage you to just go ahead and graph these and take a look at what this image triangle looks like compared to the original, just so you can see. And then letter C. Look at the rim of a car tire. To the nearest degree, find the angle of rotation required for spoke A to move counterclockwise to position B. Here's how I would do this one. So there's maybe there's maybe multiple ways to do it, but I'm just going to count the spokes, right? So starting at B, there's 1, 2, 3, 4, 5, 6, 7, and I already counted B. Okay. There's 7 different spokes breaking this area up into 7 different triangles. Okay, 7 different angles, equal angles. So what angle am I going to be required to move through to get from B to A? Well, let me think about that. That's going to be 360 degrees as a whole circle. Divided by 7 gives me one of these little angles in here in between the spokes, and then times 2. Let's just go ahead and run that through a calculator. 360 divided by 7 times 2 gives me 51.42 degrees for 360 divided by 7 times 2 is 102.8 degrees, 102.9 if I round up. So we're going to say that this equals 102.9 degrees. And that's the number of degrees required. If I were to explain it, there's a total of 360 degrees for a full rotation, but we're only going to rotate through 2/7 of that amount. There's 7 angles, equal angles in here, and I'm only rotating through 2 of them. Therefore, it's going to be 2/7 times 360 degrees. The way I did it was 360 divided by 7 times 2 is the same thing as multiplying by 2/7. Okay. All right, and then we get 102.9 degrees as our answer for that. And that is how you work these sorts of problems. Make sure you do the problem set for next time using the skills you learned here.